It's time for another tutorial. Today we're going to be talking about the advantages of C++11 over regular C++. But for those of you that are already familiar with C++ and are maybe wondering what C++11 has to offer, I know a lot of you probably don't have time to pick up a big heavy-ass book and read everything there is to know, and God knows C++11 added a lot of stuff. But I found that I'm going to cover just two things in this video, and in my opinion, they are the two best things that C++11 added to C++ to make it far less of a pain in the ass to use for game programming or C++ programming in general. So what I've done here is I've started out with just a standard C++ very simple program that constructs an SDL game loop, uses a button class that I have here to detect whether or not you're clicking a button, and then if you click the button, I make something happen. However, I've hard-coded what is to happen inside the button class because I want to show off some of these features. So first I'm going to show you what this code does when you run it. So I got a very ugly looking button. It's a low-level programmed game button, so I got a mouse, and if you click it, the sound plays. So that's the button. And what I'm going to do here is I'm going to convert this code to C++11 showing two features. Those features include smart pointers, or C++11 calls shared pointers, which automates some of the memory management and ownership semantics, and lambda functions, or lambda delegation, which are a really cool way to do local functions in C++ that were not previously available before. So before I get off on too much of a tangent, I'm going to talk about first the easier to explain of the two, which is smart pointers. So if you know the regular C++ paradigm for memory management, typically what you will do when you're doing dynamic memory, which involves setting a pointer equal to the return of new, whatever object you're allocating, and then when you're done with that object, you'll call delete on it. After you're called a new, and then you use your object for a little bit, if you forget to call delete, bad things can happen. Namely, you can leak the memory at best, and at worst, you could forget to deinitialize your whole system, and your game won't shut down properly. If you do this in the middle of the game, for example, suppose this isn't a game loop, but it's an entire level of a game, and there's 30 levels or 60 levels in a row, and you forget to call delete every single time, eventually you're going to use up all the memory on the laptop, and you're going to piss off whoever's running your program, and it's going to suck. And that's generally regarded as a bug. Now, I had done C++, standard C++, not 11, for like 10 years. It's basically it spanned most of my game programming hobbyist career. I've been writing C++ longer than any other language I've learned, and so it's ingrained in my head to never forget to call delete. However, in the last couple years, I switched over temporarily to other languages like Objective-C and Swift, doing iOS and Mac programming. And in those languages, they have higher level memory management paradigms out there, namely reference counting, which forego you having to call delete, and basically as long as there's a pointer to the object, that object will be alive, and when the last pointer to that object goes out of scope or is released, the object gets released. And I started realizing that's a really damn good idea, and that's a hell of a lot easier to work with than dealing with, well, when do I call delete? Am I deleting it when someone else still needs it? How does this work? So C++ people decided that was a great idea too, and they basically took the idea from a library called Boost, which implemented it using very ugly template semantics, and built it into the C++11 standard. Let me show you how that works if you're not tired of me talking about it enough. So you include a special C++ header. I believe it's called memory. No .h, just memory. And then it becomes part of this std : namespace. So in this case, I can now actually declare game loop as a smart pointer using standard : shared pointer, game loop as the template argument, and then set that equal to a call to new game loop. However, I wrap that in standard shared pointer constructor argument like so. Now I have a pointer to game loop, and calling delete is no longer necessary, because when game loop goes out of scope, it'll know and it'll automatically free the object. So let me show you what that might look like by going into my destructor and putting a breakpoint. Here's my game. Return from main. If we look at the callback loop, there's a bunch of really crazy stuff, but long and short of it is basically once main returns, the only reference to game loop goes out of scope, and game loop gets freed automatically, even though I forgot to, and in this case, it would be an error to call delete. That's pretty freaking awesome if you ask me. So there's a couple things to make this not so bad, and I'll explain it. First off, this syntax looks like shit. Compared to like the way Objective-C does it and Swift does it, you shouldn't have to go through all this double colon shared pointer crap just to create one of these. So typically what I do is I type def some of this crap out of the way. So every time I have an object in existence that's going to support these smart pointers, what I will typically do is a number of things. For starters, I'll include memory in their header file. Usually I'll put this in a place that gets included somewhere else so I don't have to put it everywhere. Then I will use this special derivation where basically I will actually do public enable standard double colon enable shared from this. It's the stupidest name in the world, but once I put this in here, it allows some optimizations that I'm about to explain. And for some reason, it's not coming up as a thing. I don't know why. Hold on. Expected class name. I'm giving you the class name, you idiot. Alright, so the standard enable shared from this is something that is not required, but I'll explain why it could be useful in a bit. And the most important part is I will type def two different parts of pointers, and I'll explain what these are too. Basically what I'll do is I'll say pointer is equal to shared pointer of myself, and weak pointer is equal to weak pointer of myself. Fun thing about type defing is I always get the damn order confused, even though I've been doing this for years. And then of course I still manage to forget semis too. Alright, so what that does is allows me to change this line here into something that looks a hell of a lot better. Basically what I do is I say game loop pointer game loop make shared game loop and the constructor arguments. And if I don't have namespace used, I have to put standard double colon in front of that. And you'll notice still works all the same. Now, if I wanted to be really concise, I could say using namespace std. That's not news to anybody. And then basically I've shortened the thing into something very simple. I think that's a hell of a lot easier to work with. And in my game, I use these double colon pointer type defs everywhere in place of where I used to use the actual pointer. And what's really neat about shared pointers I didn't talk about is that the arrow notation works the same. It's basically an operator overload. It knows how to break right into the object, and smart compilers like Xcode even know to autocomplete through that too, which is really cool. So what's enable shared from this? Basically, it allows make shared to work, and it also allows one allocation to be done instead of two separate memory allocations, which are typically once for the object and another for the shared reference counting table. And in C++, it's just considered bad practice and leads to memory fragmentation when you don't consolidate your memory allocations. It almost never makes a difference on big, heavy objects like game loop, but if you're going to be doing an architecture that depends on smart pointers propagating everywhere, you want to get in the habit of doing that to lower your overhead. Okay, so what did I really do here? I did some type defs and I allowed myself not having to deal with calling delete. Well, what's the big deal about that, right? Well, where the magic of smart pointers comes in is when you actually pass them around how they function. Like I said, these are reference counted pointers, and the best way that I can describe what a reference counted pointer is if you were to think about, so there's your memory, And these are your users of your memory. These are your smart pointers. And basically, every single time that you create a pointer and assign it to the memory, it creates, basically, you can think of it almost like it's a balloon. It's a line attached to the balloon, and it prevents it from floating up into the sky. Every single time you assign a new smart pointer, using the trackpad for art is amazing, by the way. Every time you assign a new smart pointer to the object, you create a new reference to it, and regardless of the order of those smart pointers being reset or going out of scope, it's only, this is awful looking, it's only when the last one is erased that the last tie is cut and the balloon goes up into the sky and the memory is free. That's the way I always think of reference counting pointers. I should save this. This is a masterpiece of artwork. But anyway, so let me show you what I mean by that. It's a little hard to show with this game loop idea. So what I'm going to go ahead and do here is create a class real quick called just banana. And what banana is going to do is it's going to log when it's been destroyed. Good. I'd be willing to bet money that I did not include IOStream. So I stream, you stream, we all stream for IOStream. Let's get that in there. All right, so there's banana. Always forget that semi at the end of class declarations. So the idea here is that if I was to create a couple of these, and I'm just going to do this up here before I go into the game loop. So I'd say, oh, pointer notation again, because this is useful. I know I'm harping on this, but I really want to make sure I get the concept across here. For those of you that are familiar with what ARC is or what automatic reference counting is automatically, and you already get the point, you can feel free to skip ahead. But for those that are not, this will help explain it. So basically, banana pointer b make shared one of these, no arguments. So there's one, right? And immediately I reset, which is also, I think is nicer. I could just set it equal to null pointer. So basically, it's only between these two lines that b exists. And I can prove that by a couple things. If b, it exists. So what we should see in the log output is it exists, and then the hoot, because it's been freed right afterwards. So the idea here is if I were to have a function in here that would take one of these as an argument. Now, I'm going to give this another name. Ban. Now, as long as that function has that pointer, that second reference, the object will be kept alive. In other words, if I were to check it like so, call it as an argument to this function, it gets passed in. Now I'm going to do something a little nuts. I have a global up here, so there's going to be temporarily 3 of these. And this is just going to be called G banana. I don't have to initialize it to null pointer, they automatically do. It's just my C habits kicking in there. So this is going to be a little weird. Some function is basically going to set the G banana equal to ban. And then when I call null pointer, or when I set b equal to null pointer, there's still going to be one of those references left, which is namely the global one. It'll go from 1 reference to 2 references because there's an argument, to 3 because I set G banana equal to ban, back to 2 because ban goes out of scope when some function returns, back to 1 because null pointer, I set the original local variable b to null pointer, and basically what I'm going to get printed here is it exists, but because that global is just staying set there, it'll never get deallocated. That's weird. Oh, that was stupid of me. Hold on. There we go. So it exists and it doesn't get deallocated, which is rather odd, right? Now, of course, if I immediately after that also set the global one to null, then the last reference goes down and it gets freed. All right, so you get the idea. It's basically pretty hard to screw up when you're using these kind of pointers. They prevent things from getting out of hand. And what's really neat is if you want to make sure that you get a reference to an object, but you don't want to have that reference keep the object alive, a safe way to do that is to use the other side of smart pointers, which are called weak pointers. And what these do, they're very cool. They allow you to, like I said, get a reference to an object without keeping it around, so you can check to see if it's alive. But if the last strong reference goes down or the last shared pointer goes down, then the object, the weak pointer, will automatically be set to null for you, which is very cool, and it's a way for you to be safe. So now you can see it's the exact same paradigm. However, I got some errors here. Namely, you can't use a weak pointer without locking it, which actually returns a shared pointer, which is the locked version of it. And then, if and only if the lock pointer is valid, you can use it. So you might say, like, it exists, and then you would do gbanana.get lock get. If you do .get on a shared pointer, notice not arrow get. It's not a method on the object. It's a method on the pointer. It'll just return the C pointer, the standard pointer, for you, if you cared. So that would print it exists if it did exist. Also, another thing that's annoying, you can't set smart pointers directly to null pointer. You just have to call .reset on them if you wanted to reset them. However, you're going to see in this case that it exists won't get printed because at this very line, this is the last strong reference going down, and therefore the hoot already happens before, and the weak pointer is inexistent. Now, if I were to move this up before I set it, I would get access to it because there's a strong reference to it, and of course, I'm able to see that it still exists. So that's the basic gist of how weak, or really smart pointers work, both the weak and the strong ones. And I'll explain a little bit why, well, you kind of get the idea of a little bit why weak pointers need to exist, but I can talk more about that later. So I'm going to literally just get rid of all this proof of concept code and go back to my game example here. All right. So basically the idea is if you're migrating to C++11 and you have a new team of engineers and maybe they're not that adept with the old school C++, maybe they were never that good at delete, they're error prone, they cause memory leaks, so there's a lot of crashes, it would behoove you to migrate some of your code, if not all of it, to these smart pointers, especially if overhead is not a concern for you. And I can prove that I've used smart pointers everywhere in my most recent game, and it does not affect performance that negatively. If anything, OpenGL is the barrier. How many polygons I'm drawing is the bottleneck, and not smart pointers. So if somebody tells you there's too much overhead in them, I would beg to differ. So when you're migrating your code base to C++11 smart pointers, you want to basically look everywhere that you've got regular pointers to C++ objects and swap those out for the smart pointers where possible. Notice I'm not, and I can't do this with the regular C objects because those would not, they just can't be adapted to use these pointers. So your SDL window, renderer, fun, anything that's a C object, those should be left alone. But C++ objects are higher level, they're more expensive, and it's a good idea, to adapt those. So the first thing you want to do is if it's a new object that you've never adapted before, we've already got game loop, but we've took care of that. Button is a new object, you need to do the type def. This is optional, but like I said, it makes your code a hell of a lot more readable. So I'm just going to paste in these type defs. I'm going to include memory up here in case I need it. And I'm going to paste some template arguments in. And now, weak pointer is also something I don't always put in, but I've gotten in the habit of doing both because you never know if you're going to need a weak pointer. So you adapt the class in the header, and then you replace button with button : pointer. This isn't always something you do. There might be a case where you want to use a weak pointer instead, but I know that this is the main ownership pointer. And then, of course, I replace the button assignment with make shared instead, and it works just like so. I said it works. Oh, hold on. I really should use namespace std up top. Oh, cannot delete expression. Well, of course you can't. This is now no longer necessary. It'll happen automatically. So you can just remove the delete line. And you'll see that the button destructor, which I'm going to put a breakpoint in, will automatically get called when the rest of the stuff goes down. So there's kind of a trickle-down effect here. Basically, we have main drops the game loop drops the button, and then the button destructor is called. This trickle-down deallocation works beautifully. I've been able to, in my own game, have hundreds of objects that hold on to gigabytes of memory all go down properly just when I just swap out the classes and load a different level in my game. I really love an architecture that depends or is based off of this automatic reference counting stuff. So I wanted to keep this example simple, so you're actually going to see that I'm rather done in this small example because I only have 2 C++ objects in the entire project, which is basically a game loop and button. However, if you were migrating a real game engine, you wouldn't be done for hours. But I wanted to show you that. So we've covered one of the 2 biggest things I wanted to talk about today, which, believe it or not, is actually the simpler, which was shared pointers. So